Welcome to this pre-recording of a talk on GPU Newton to compute power series. So this is a preliminary report in the sense that there is not yet a preprint available, not yet at the time of this recording. It's also a software project, so all software used in the computational experiments is available on GitHub, released under the GNU GPL license. And I always acknowledge the funding agency, the National Science Foundation. This is a relatively short talk, and in order to keep it streamlined, there are two parts. In the first part, I will try to explain the problem statement and the goal to use graphics processing units to compensate for the overhead of multiple double arithmetic. In the second part, I will get into the computational results after explaining the setup and also the main ingredients of the algorithms. Okay then, what is the problem? We want to make the computation of power series scalable. That means running this for thousands of equations and variables, and we want to compute these power series accurately. So what are the two main bottlenecks when we run Newton's method? Well, we have to evaluate and differentiate the equations, and that requires convolutions because we do this at power series. The power series again lead to a lower triangular block Toeplitz system. So we have to solve in each step to compute the updates of Newton's method. We have to solve also a structured linear system. So these are the computational bottlenecks. So this makes that this is a very computationally intensive work. So we are having two concerns, realizing performance and at the same time convergence. Both of these concerns will impose some regularity assumptions on the input. So this is a multi-dimensional problem. We have the number of equations, number of variables as the leading dimension, but then there is the order of the series. So we do not work with series that go on forever. We truncate at some spot. And then we must use extended precision, so we can also see what happens when the level of precision doubles. What happens to the overhead? Okay, so on this slide is the drawing of a task graph originating after a linearization of our problem. So instead of working with vectors of series and matrices of series, we look at series where the coefficients are vectors and matrices. That leads to the triangular block Toeplitz system. And the task graph here defines a coarse-grained parallel execution of solving such one triangular block Toeplitz system. So the arrows give the flow of the data. Statements that are on the same line can be executed in parallel. So one can compute from this task graph the maximum speed up that can be obtained in this coarse level grained parallelism by computing the length of the critical path in this graph. So for GPU acceleration, we are not following this scheme, but this is kind of a nice representation of the algorithm to solve this system, which is needed for one update of all the coefficient vectors of the series. All right, I'm citing here a reference, a historical reference, which addresses the convergence. In order for convergence, the leading coefficients must be computed much more accurately than the next coefficients. You can also see this as follows. If you are losing 2 decimal places in your answer in every term of the series, then if you are working with order 8, you can already lose 16 decimal places. And that's then even with, say, a very well-conditioned Jacobian matrix. So multiple double precision is used, multiple double arithmetic. A multiple double is an unevaluated sum of doubles. So it has the nice property of predictable overhead. And also we are still doing numerical analysis. So if the result can be represented exactly in the leading in a 64-bit double number, then the second double represents the accuracy of the result. And here you see with double, double, quad double, octo double, we go from 32 to 64 to 128 decimal places. The software that is used should be acknowledged. So this project could not have been done without QDLib and the Campari software. Customized software is used in the sense that it's very natural to represent one quad double as a vector of or an array of 4 doubles, but instead, and then a vector of quad doubles as a vector of arrays of length 4. Instead of doing that, instead of working one vector of quad doubles, we will work with 4 vectors, with 4 arrays. The first array be the array of the leading doubles, and the last array, the 4th array, the array of the least doubles. This has significant advantage as far as performance goes. The CUDA development kit exports double 2 and double 4, but if you want to go to octo double, there is no double 8. So you cannot really, for efficient memory coalescing, you can actually not really exploit that any further past real quad double. The table that is given here represents kind of a very basic estimate on the cost overhead. So this table is used to compute the amount of floating point operations that we do. The number 439 as the average for quad double is kind of also an indication that when we are having teraflop performance, that we can compensate for the quad double arithmetic. Teraflop precision, teraflop performance that can be achieved with the modern GPUs. Here's some important related work. So there is the MP LAPAC, which supports, so the middle reference here, which supports quad double linear algebra operations. And this effort is certainly already more than decades old. The multiple double precision is not real multi-precision in the sense that if you want to work with 23 bits of precision, for example, well, you can't, then you cannot do this. So there is here this related work which has true multi-precision arithmetic and which offers a very nice comparison which is favorable for the multiple double arithmetic. So certainly for double double and quad double arithmetic, that type of arithmetic appears to be the winner. I should also mention that the list here is restricted to the efforts of increasing precision. So there is the current trend of maxed precision in high performance computing, which is more oriented of using float and half float precisions, trying to really use the least precision as is necessary for accomplishing a certain result. Here we go in the opposite direction. Okay, the bottom line on this slide is that we can have teraflop performance. GPUs are capable of performing 1 trillion floating point operations per second. If one has CPUs running at gigahertz, that giga means billions, so then typically one would express performance there in the order of several gigaflops on one core of a CPU. So my experience here will be restricted to Pascal, the P100, and the Volta, but also the more recent GPUs are even more powerful. The other important point is that with multiple double arithmetic, the computations become compute bound, and one really gets to take advantage of the massive parallelism offered by GPUs. Here is some prior work. I mentioned the task graph earlier with the coarse-grained parallelism as you would do on a multi-core chip. I explored this in a publication 2 years ago. There are the two main bottlenecks, the evaluation and the differentiation, and then the linear algebra. So this has been described in 2 other papers. So most of the GPU work appears in IEEE publication. That doesn't mean that it's certainly not that it is not mathematically interesting. Far from it. Okay, so this concludes the first part of this presentation. So let's now get into the experimental setup, which uses monomial homotopies. So look at the example. We have one column of monomials at the left side and one column of power series at the right. So monomial homotopies have no practical benefit, so one does not need Newton's method to solve these. But in the current study, which is a bottom-up study, first try with the most regular, with the most simplest systems. If we can't do those, we shouldn't continue. So we first start with those problems. So the solutions are exponentials, which have quite an interesting power series. To make it a little bit more interesting, there are these alpha parameters which allow us to modulate the growth of the coefficients, which introduce some variation in the solutions. Why do you actually need now again use multiple double precision? Well, look at these exponentials. We have the factorial coefficients, and these coefficients, if you want to represent all the coefficients of the series in, say, the same scale, we have the leading coefficient, which is 1. But then the least coefficient, so say for order 64, is already 10 to the power minus 88. So if you use uh, quad double precision, then this is already less than the 10 to the power minus 64. So you may actually, unless you of course know that you are computing exponentials, but in just the honest setup, you cannot actually hope to compute the series accurately unless you use octodouble precision. So this table here, which is kind of a back of the envelope computation, kind of illustrates the need for multiple double precision. I have some experience with hexadoubles, and there is still that ongoing future work that will happen. Once also I get my hands on the more advanced, the latest, the newest generations of GPUs. Okay, so monomial homotopies are not so interesting, but you can immediately extend them in two-column families of systems. And it does not take too much work to see that any general polynomial system can be represented in this two-column format if you allow for the introduction of extra variables. So I'm not advocating that anybody should do this, but the two-column representation is another way of scaling this. 64 is the order of the series, and also 1024 will remain fixed as the dimension. What we will see as the increase is actually the increasing the scalability in the precision. And each time as your problem becomes more and more expensive to compute, how much of that can be compensated by the acceleration by the GPU. Very high level description, 6 different types of kernels. So the convolution, that was a separate paper. The least square was another separate paper. So the householder QR consists of many kernels that define, but for the purpose of this talk, the householder QR is considered one type of accelerated computation. So the question that I will try to answer experimentally, of these 6 different types here, which of the types is actually now most expensive or most important? So we work typically with 64 series, 64 blocks of coefficients. In order for Newton to converge, you have to start with your leading block that it is already half of its precision is correct. So if you work in octodouble precision, you have already 64 decimal places that are correct. Otherwise, you will not have convergence. It also does not make sense to immediately and every step work with 64, series of length 64. So the order will be increased gradually. And you hope for quadratic convergence. So the formula that is here in the second item is kind of hoping for that quadratic convergence. That is a stop criterion. Once a block of coefficients is correct, you will notice this when you evaluate. If the right-hand side evaluates to 0, then the QR in the update will also give a 0. So you don't need to do that solving. So this gives a stop criterion. The decision to continue launching kernels is made by the host, and that is based on a single number or limited number of doubles. So the memory transfer between host and device is also hereby quite limited. most of the data can stay on the device, unless, of course, for testing purposes, one wants to compare. Okay, so I have developed this new algorithms on the Volta, and the Pascal is used for comparison. So the Volta is 1.68 times faster than the Pascal. So one would hope that if they are both running at full occupancy, that you would notice that. Notice also the massive parallelism. So the 64 as the order of the series is not a coincidence. There are 64 cores per streaming multiprocessor, giving on Volta a total of 5,000 cores running at 1.9 gigahertz. The MacBook Air Intel has processors run at 1 gigahertz. Think about what you would do with 5,000 MacBook Airs. So if you think that GPU programming is hard, think about the efforts that would need to be done with 5,000 laptops. So how do we see floating teraflops performance? Well, we accumulate the number of arithmetical operations in helper functions, and this gets then compared with the timers. Okay, now let's look at some experiments. So we had the 6 different type of accelerated computations. Convolutions have to be done in every step. The QR is only done once. So this is why the QR, I exploded the slice here. So the linear system solving in the least square sense is done initially only once with the QR on the Jacobian matrix, the leading matrix in the matrix series. And the QR is then recycled in every step. But even the back substitutions that happen very frequently, they do not occupy much of the pie. The updates are important, and also the residuals. So the residuals are here computed in full. So there is the b minus a times x, which is computed for all 1024 equations. An obvious speed up is to do this only for a couple of equations or only for one random choice. Typically, if there is no convergence, if the residual is large, you will already notice this at one well-selected equation. So this is a first preliminary experiment. The pie shows where the future optimizations will need to go. So residuals is definitely the targeted area. Okay, wall clock. I have scheduled this for a talk of 25 minutes and I'm getting very close to this. So the wall clock is most important. So the wall clock, so this is a 2-log plot. So if we look at the red bars, one sees that when one doubles the precision, the height of the bars increases by 2, which means that, or at most, which means that it doubles less than that. That's very important. So doubling the precision with doubling the amount of time is kind of surprising that you can do that. But observe the blue bars. The GPU gets more and more busy. So the GPU gets quite fully occupied when you get to quad double precision. So that's a very important result here. Running this for dimension 1024, one column of monomials with order 64 of the series on Volta. The full 24 steps. Okay, so convolutions occupy a significant slice of the pie, almost 1/3, and that's actually quite good because of performance. At degree 40, we have already teraflop performance. So the Volta has 64 cores per streaming multiprocessor, and this kind of explains that after 40, you kind of get a very good performance. Okay, so then comparing GPUs, one does this at the teraflop level, making sure that they are fully well occupied. Here I picked the householder QR and for quad double precision, where the 1024 is tiled up in 16 tiles of 64. This is better than 32 times 32. So this is certainly not optimal, but the performance ratio is 1.44. The last line indicates the what the effort of the RTX, which is in a gaming laptop, also not the newest GPU, but still a very powerful and very useful graphics card. So GPU computing is often seen as personal supercomputing. And I mentioned laptops earlier. If you have very powerful gaming laptops, then a lot of it is also reproducible with the software that is publicly available. Okay, I'm running out of my budgeted time of 25 minutes, but still within the half hour. The bringing high performance computing into polynomial homotopy continuation is still something that is a work in progress. So for polynomial homotopy continuation, and in particular to apply analytic continuation, we need multiple double precision. If your order is 64, then you can get by with octo-double precision. Teraflop performance is achieved with evaluation and differentiation, one of the important parts of the pie. And for practical purposes, where one is concerned about wall clock time, doubling precision less than doubles. So just because of the nature of the suitability for GPU acceleration. So I thank you for watching this presentation and for your interest in this work.